Hello, my Gen Chem students. Let's talk about some kinetics. All right, we have gone through most of the chapter. We did the rate of reaction equation, we did the rate law equation, we did the linear equations. Now, just a minute, I have to make sure I didn't do it yet. Now we're going to talk about the models for the reaction rate and a very important thing called activation energy. The activation energy is probably the most important thing you should know about a reaction because it will tell you how much energy it's going to take for it to get started. And we have a couple of theories to figure that out. All right, so we're going to do the collision model theory, and then we're going to do the transition state model theory. Well, why in the world are there two theories? No theory usually covers 100% of all the details. And so we just have two, that are very complementary to each other, but they approach it in a different way. All right, so the collision model theory talks about, surprise, whether the collisions are effective. So you have to have the proper orientation and you have to have the correct amount of kinetic energy. Now, in class, I would be using my hand and it would go into my fist, would go into my palm. Okay, proper orientation means, if you will, lock and key mechanism. All right, there's a really ugly lock. So let's say those are our two molecules. They must find each other in this orientation. Now, are they always going to be in that orientation? No. So maybe one time it's like that. Okay, they do have to align so that they can properly react. But they must also have the kinetic energy that they will bump into each other and actually form a reaction. If they have too much energy, sometimes they can just bounce off. But if they don't have enough energy, the reaction is never going to be started. So the orientation is very vital, but it's the kinetic energy that we really want to talk about here. So those colliding molecules must contain a minimum amount of energy to make or break bonds, okay? And we call that the activation energy. So E subscript A. It is unique for every reaction. It is like a fingerprint. Every reaction is different. Every reaction is unique. And it's also always positive. Okay, this is the energy you have to put in to get a reaction going. Okay, you're not going to get energy out to get a reaction going. So it is always, always, always positive. All right, and like we talked about above, it has to take into account this orientation, this kinetic energy. And so this is our wonderful little rate constant, okay? So our little k, the steric factor takes into account the overall orientation, and that is hard to predict. But we can say that if it's really cold, they're not moving around or orienting themselves as quickly. Okay, Z is the collision frequency. Do you have really high concentrations? Is it temperature? What is controlling how many are actually taking place? That is calculated using the kinetic theory of gases. No, you don't have to calculate it. And then F is the fraction of collisions that occur with at least the minimum activation energy, if not above. So really it's the F part that we are interested in. What is that minimum energy? So these are kind of lumped together. And E to the negative EA over RT. That is its exponent. That's its exponent. Okay. All right. Well, the transition state model is pretty much going to say the same thing, but in a slightly different way. So the reactions form transition states. Okay. Before they collided and they either made new bonds or broke bonds. Here, we're going to actually visualize some kind of intermediate, and the intermediate implies that it can be isolated. So the word transition state is something that we visualize, but you can't isolate it. Okay, so that's very important. There is a difference between those two words. All right, it's an activated complex. If you can isolate it, it's usually an intermediate, but I'm going to use those terms kind of interchangeably. In organic chemistry, it's very important to talk about. Can you isolate it or not? For us, it's just some kind of intermediate. It is in equilibrium at low concentrations. It may choose to go on and form products, or it may decompose back to the reactants. And here's the power of this theory. It allows loosening or weakening of the bonds or making the bonds rather than just collide, whammo, it's done. Okay, so that's really its power. So exothermic, yes, negative delta H, heat comes out. If you have your reactants, there's a minimum amount of energy and then it goes down. So if you'll notice, this one is lower. That means energy, and in this case, heat, comes out. But you still have to pay the cost. How much energy do you have to put in before this can even happen? That's the activation energy. Well, how much energy you're going to get out? Just that. That is the useful. Okay, you pay this one in, you get that same amount back out, but this is the useful. That is for exothermic. Well, what about endothermic? So endothermic, you still have to pay the cost to get to that intermediate, but this one is higher. So you still have to pay this cost to get it going, but guess what? You only get that much back out. So you have to supply the rest of the energy to keep that reaction going. So there's a couple energy diagrams, and here is one with numbers. All right, so we're going to take carbon monoxide and we're going to take nitrogen dioxide. This is a visual, okay, the double dagger up there means it's a transition state. That is a visual that says, okay, they're going to come close together and going to start forming that bond, and we're going to kind of loosen those bonds. Okay, it's a middle state. It's a transition state. It can either fall back apart to reactants, or it could go on to products as long as it has the minimum activation energy. So up we go, and then down we go. So this one is lower. And if we're talking about heat, it would be exothermic or exogonic, meaning energy comes out. Here's how much you have to pay. Okay, there's the activation energy. Here's how much you get back out, and here's your extra. So this amount right here would be 134 kilojoules plus, is that a 226? It's awfully hard to see. All right, so that would be 310, 106, 360 roughly. That's supposed to be a kilojoule. Don't know what I was writing. But you don't get all of that back out because you've already paid. Okay, so think of this as the net. Okay, you have to put some in, you get that much back out, but how much profit, I guess, did you get? All right, so there is the idea behind the transition state theory. What is that going to mean? Well, we need to figure out how to determine the activation energy, and it is dependent on temperature. So we're going to play with a calculation using temperature. So the rates of most reactions generally increase with increasing temperature, and they decrease with decreasing temperature, which should make sense because the collisions, you have to give them energy to get in the right orientation, and then you have to give them enough energy so that if they do collide, they have the minimum amount to go on and react. And temperature is usually the energy of choice, specifically in the lab, so we can control it by temperature. If you increase the temperature, you increase the rate. If you decrease the temperature, you should decrease. And then here's a nice rule of thumb. If you increase the temperature about 10 degrees, it doubles the reaction rate. Okay, that's a nice rule of thumb. So think of it this way. Your wonderful potato salad is sitting out on the picnic table and it's 100 degrees outside. That is spoiling a lot faster than if you're in the park eating your potato salad in the middle of winter. Why you do that, I don't know. But that way it would be colder, and so you would slow down the spoiling process. Okay, 10 degrees to double a reaction is very significant. We spend a lot of money, okay, a lot of money to avoid this. Oh, what do you mean? Refrigerators, freezers, and then increasing the temperature, microwaves, stoves. Okay, we love to play with kinetics. All right, there is a very important equation called the Arrhenius equation, and it is going to tell us the activation energy. Okay, so this should look familiar from before. Well, these are constants, and we're going to give them the capital letter A. So the rate constant is equal to this constant times e to the negative EA over RT. Well, let's integrate from 0 to time t, and look what you get. Another linear line. Now, if I rearrange that into y is equal to mx plus b, it's the natural log of k is equal to the negative EA over r. The independent variable is 1 over or inverse temperature plus the natural log of A. And look what this is. It's the slope. So we can actually find the activation energy off of a graph. Now, what if you don't have a whole bunch of data points? Well, you don't always have to go to the graph stage. You could just subtract them from each other. Okay, so this is called the two-point equation. That's nothing special to us. That's a mathematical thing. If you only have 2 points, you could plug them in initial conditions, final conditions, and you can solve for the activation energy that way. But we like to use graphs. So let me see. Do I have a graph here? Sorry, gonna make you seasick. I'm gonna go make a graph. Remember the kinetic chart handout? There's a few of them that are these types of graphs. But I'm just going to go to the whiteboard. All right, what are you going to see? The key to an Arrhenius equation is you have to be looking at the axes. This would be the natural log of K. Yes, you've seen natural log on the y-axis, but that was the natural log of a concentration. This is the natural log of a K. Sometimes I include the units. If I include the units, you can tell the order. Okay, the graph is not going to tell you the order. The units would tell you the order. And then on the x-axis, it would be 1 over the temperature in Kelvin. All right, and you would see a wonderful straight line. If that's true, then we know that that slope is equal to the activation energy over the gas constant. Now, this gas constant needs to be in energy units. So that is 8.314 joules per Kelvin mole. So that's the one that we're going to have to plug in. So again, I'm making up these numbers completely. So if the slope comes out to be a negative 25, well, I'll just say 25,000. Okay, if it comes out to be a negative 25,000, can you get my activation energy? Why, yes, because negative activation energy over 8.314 joules per Kelvin mole is equal to a negative 25, 1, 2, 3. And remember, the units will not come off the graph unless you interpret it. And sig figs for us, if you're taking data off a graph, we're not going to worry about sig figs. Take at least 2, 3 would be better. Okay. I actually have 4 right here, so I'll probably keep 4. All right, let's go ahead and solve. So multiply both sides by a -1. So my activation energy is equal to 25,000 times 8.314. Remember, this graph is K versus T. So I know it's going to bother you, but the mole and the Kelvin actually go away. Those are canceled by the natural log of K and the inverse temperature. So your answer is going to end up in joules, which we were expecting. And it's a big number because we usually deal with, kilojoules, not just joules. So this is going to be really big. Let me get my calculator. And 8.314. We are going to get 207,850 joules, or 207.9 kilojoules if I kept those 4 sig figs. And if you'll notice, the sign comes out positive. The sign comes out positive. And that's the way you would do the Arrhenius equation. All right, I'm trying to decide. You know what? We're going to call that one good, and I'll do one final video on kinetics, talking about catalysts and reaction mechanisms. So before I leave this one, we're going to go back and do one look. Just a little summary. Arrhenius activation energy. The whole purpose. The Arrhenius equation. And remember, the activation energy came from K is equal to A E to the negative EA over RT. Remember, that took into account, all the collisions and all the orientations. This is going to be the natural log of the rate constant. This is going to be 1 over temperature. Slope equals a negative EA over R. Jolly, you just said all this. Yes, I just wanted to kind of do another clarification. You are only going to use this graph to determine the activation energy. B does equal the natural log of A. Remember, A was the constant all put together. So yes, this equation will give it to you. And the order will only come from the rate constant. But the thing I wanted to point out, remember, this is energy, 8.314 joules per Kelvin mole. This is obnoxious, but the Kelvin moles, we'll just say they go away because of the units on graph. Okay, I didn't say anything new there. Hopefully I just said it in a different order in case that wasn't clear. So we now have how many reactions? We have the reaction rate equation. We have the rate law. We have the linear equations. And now we have the Arrhenius equation. All right, until next time, jolly out.